of information. There's a field of maths called information theory, and these concepts are borrowed from there. So machine learning borrows concepts from many fields, and this is one of those fields. So we borrow these concepts from information theory. So what is, first of all, let's understand what is information or surprise. Okay, information or surprise. So what's the literal meaning of surprise? Let's understand that. For example, if you see a very common event, will you be surprised? No, right? And if you see a very rare event that doesn't happen, then you'll be surprised. That's how we measure surprise, right? Common events, not surprising. Rare events, that's surprising. And so what's the probability? And if you want to understand that in terms of probability, then so the probability of a common event is very high, right? So if we say probability of a common event is very high, and probability of a rare event is very low, right? That's what it is. And if there is something common that is happening in terms of information, if you want to understand, so if there is something common, means it is not providing me any much information. For example, if we understand it with respect to height of people in a country, so if most people are of average height, so if we talk about India, they're around 5, the height is about 5 feet 6 inch or something. So if I see anybody around 5 feet 6 inch and close around that 5.7, 5.8, okay, you won't be surprised. But if you see a rare event, if you see a person is 7 feet tall, or anybody who's more than 6.5 feet, that's the rare event, and that's surprising. But that gives you more information also. The rare event gives you more information, okay, that such people can be so tall also. But if something is very common, everybody is so of the same height, around 5 feet 6 inch, so it doesn't provide you much information. So that is with respect to information, that if something is very common, it doesn't provide you much information. And if something is rare, it extends your range of information that, okay, such an event can also occur. So in terms of probability, if we say, so probability, as we understand, probability of a common event is very high, probability of a rare event is very low. How do we understand it in using, how do we define surprise then? So surprise factor, this is defined as, okay, so as negative, okay, we write it as x, negative of log of probability of that event. Okay, let's understand this. Why log? Okay, so this is very useful. If you see, you will see in machine learning everywhere log is used. Okay, so that's why it's a, and this is the probability. Okay, this is to give it a range. I will not go into the depth of it, so let's take it up the face value that we are using log of the value, and let's understand the details. The probability of x. So if it's a common event, okay, probability of a common event will be very high. Say for example, if something is very common and if it will happen only. Say for example, if I have a coin which gives heads, it has heads on both the sides. So whatever you do, it will give you head. So probability of head will be equal to 1. So log of that probability. So what will be the surprise factor here? Surprise factor of this event will be minus of log of probability of x. We take log because log is a monotonic function, means as x increases, log of x also increases. We can say that, right? So as x increases, log of x also increases. So that's why we can replace x with log of x. So the probability of x will be replaced by log of x. Okay. So now let's come back to the example. So we have a coin, okay, unfair, which has head on both the sides. So probability of getting a head is 1. So log of 1, what will be log of 1? Surprise will be log of probability of 1. Means log of probability of x, probability of head is 1. So surprise will be 0. Yes, it is head on the both sides. So we won't be surprised. So that's how it is defined. And say for example, in the same coin, what will be the probability of seeing a tail? This will be 0, right? Because there is no tails at all. So if I have to measure the surprise for this, so surprise for this event tails will be equal to minus of log of 0. What is log of 0? Log of 0 is minus infinity. And minus of minus is infinity. So log of 0 is minus infinity. The graph of log is something, it comes here and it goes like this, it increases. So at 1 this is 0, and at minus infinity this is your x, this is y, or log x, y equal to log x. So at 1 it will become 0, and then it keeps on increasing, and it touches minus y-axis at minus infinity. Okay, so this is how it is. So coming back to this example, so log of 0 would be minus infinity, and negative of that is infinity. Means if you see a tail in a two-sided, two coins which has both the sides as head, you will be infinitely surprised. This should not happen. Okay, so this is for understanding. So this is how surprise is defined. So surprise of x is defined as minus of log of probability of x. I hope surprise is clear. And the same thing I talked initially, right? So that's what will give me the information also. More the surprise, higher the information I'm getting from it, from an event that has happened. Okay, both are proportional. From now I will just use the term surprise. So this is a surprise. So we have defined what is surprise factor. That is negative of log of px. Px is a probability. Okay, now let's move to the next topic. So what is entropy now? Entropy in general measures randomness. This is the word. Okay, it's a measure of randomness of a system in terms of probability, how random the things are. For example, if I have a fair die, so probability of observing 1, 2, 3, 4, 5, 6 will be 1 by 6. Okay, it's a fair die. Similarly, if I have a fair coin, okay, so probability of head is equal to probability of tail is equal to 0.5. If I have a biased coin, where I see that probability of head is higher, that is 0.9, probability of tail is equal to 0.1. So if I get a heads in this biased coin, will I be surprised more? Or if I get a tails, will I be surprised more? Definitely if I get a tails, I'll be surprised more, because probability of tails happening is very low and heads is very high. As I said, head is common, less surprise. So surprise factor for head is low, and for tails it is very high. For heads is low, surprise factor, and for tails it is very high. So it depends on the probability. So what does entropy measure? So entropy measures the average surprisal of a distribution. So all these are distribution, these are uniform distributions, right? So this is uniform distribution. We have studied this. Uniform means all the values are equally likely. Here also this is a uniform distribution. Heads and tails are equally likely. But this is a biased, this is not equally, this is biased. Okay, so let's now calculate let's define what is entropy. So this is what is entropy? How do we define that? Entropy is an average surprise of a distribution. This is it measures average surprise of a distribution. Distribution is this distribution that I'm talking about. This is uniform distribution. Okay, similarly we can have Gaussian or whatever, all the distributions that we know. So this gives me the average surprise of a distribution. Okay, and in terms of information, we can say that how much information do we get when we see a particular event? How much more information is this event providing me? So that's what entropy means. Okay, and if the events are more uniform, means everything is very equally likely, so the entropy will be more, because everything is like in heads and tails, right? If this heads and tails like both are equally likely, so the entropy will be more randomness. I can get a head or a tail, or head or a tail, I don't know, its chances are 50-50. But if I have biased coin where 0.9 probability I can get heads, means this is the entropy of this is low, because mostly I'll get heads and tails I'll get very few times. So the randomness there is very low because heads is dominant and we know that 9 out of 10 times I'm going to get head only. It won't provide any much information also, because I know it's a biased coin. Mostly I'll get head only. 90% of the times I'll get head only. So this is less random than this, and entropy is a measure of that. And if we write it in the terms of formula, how do we write that? So the symbol is, we write it as h of p. Okay, the symbol is h of p. P is the distribution, underlying distribution of that event, is equal to, let me write it, is equal to the expected value. Okay, expected value of the surprise factor, of the surprise what we have. Let me write it this way. So this is the expected value of, so the expected value we know, right? Expected value is the average. So the expected value will give me the average of this. So expected value of the surprise. This is my surprise factor. Let me write it down. You have seen this is surprise factor. So what is the average surprise of a distribution? It gives me this. And this is, for example, this P is this, that X has the underlying distribution of X is P. Okay, that's the probability distribution of X. So what is the expected value? We know the formula, right? Expected value of something is, so this is a negative. Remember this negative sign, don't forget this. Negative summation of all, because it's the average, right? So summation of probability of X into log of Px. Okay. So this is the formula for expected value. Probability of each event into, and this is surprise factor. This is what we are calculating. This is the expected value of log Px is log Px into probability of log Px of that event. So this is how my, and with a negative sign, because this is coming from the surprise factor. So this negative sign gives me the surprise. I hope this formula is clear. Let's understand this with the example. So this is my h of p. This is your entropy. Entropy. Okay, this is probability of X, self-explanatory, and this is your negative surprise factor. Okay, so let's see with an example. So again, we'll come back to the coin only. That's a simple example. So for example 1, toss a fair coin. Fair coin. So probability of heads is equal to probability of tails is equal to half, or 0.5. This is a fair coin. So what will be the entropy? So first let's calculate the surprise. What will be the surprise for this? Surprise is equal to surprise of heads. Okay, let's do of heads first. Is equal to minus log of probability of head. This is equal to minus of, what is the probability of head? Half. And let's assume all these are information theory. So everything I will take it as on the base 2. Okay, because 0 1 0 1. Okay, so I'll take it as log of base 2, and this is 0.5. 0.5 can be written as 2 to the power minus 1. This is 2. So this minus 1 comes in front. So this is minus 1 into minus. So this, you see, right? Minus 1 comes here. So minus minus plus, because log power comes here in the front, right? I hope you remember log. So this will become log 2 of 2. This is equal to 1. So surprise of h is 1. Similarly, this is half. So surprise of tail, similarly, surprise of tail will also be 1. These are all log base 2. I'll be discussing all these examples today that will be using log base 2 only, because that's from information theory. And this is measure. So this is 0 and 1, right? To measure, because information theory, everything is bits. And this is also measured in bits. So this is 1 bits. This is a unit of measurement of surprise. And everywhere, wherever this surprise will be there, right? So that is the unit coming out. Everywhere we'll measure the things in bits only. When the base is 2. When it's natural log, the unit is different. I don't remember now. Probably I'll write it down, or you can check it. Surprise of tails is also heads. Surprise of tails is also 1. So we saw this. Now let's take the second example. Biased coin. Probability of heads where is 0.9 and probability of tails is 0.1. So what will be surprise for heads? Surprise for head will be minus log of probability of head, that is equal to minus log of 0.9. What is log of 0.9? Of base 2. Will be calculating on log of base 2. So you can calculate that easily. I have this, but I'll just show you how to do this. Future I will just use it. That is log 2.9. So this is equal to minus point, and that minus is there, right? So that is only for log 2, and that negative is there. Negative is there. So this will be equal to 0.15 bits. So if you see this, it is very low, very close to 0. It is close to log 1. Log 1, 0 is like no surprise. So this is very close because 0.9 is very close to 0.1. So getting a heads is very low surprise. Okay, low surprise, very common because 0.9 is there. So this is here low surprise, common. Similarly, what will be the surprise for tails? Is equal to, I'll just write it down, log of 0.1. This will be equal to log of 0.1. Let's calculate that again quickly. Minus log 2, 0.1, that is minus 3.32, and with the negative sign this will become 3.32. So 3.32, okay, is very high. Okay, this is very high. This is because 0.2 is rare. 0.15 against 0.12. This is rare. So this is our surprise. And now let's calculate the entropy for each of them. So for the example 1, okay, entropy of fair coin will be equal to, this is equal to minus sigma probability of x into log of probability of x. We saw here, this is your formula. Okay, so let's use this formula, fair coin. This is, so what will be the sigma, all the possible, over all the possible outcomes. So heads or tails, there are only two outcomes. So what will be the what will be this? This will be equal to, I'll just write minus outside, and then probability of x is 0.5 into, then that was, what was the probability of, both are 1, right? Here both are 1, here 1 and 1. So minus probability because of this minus 1, this was 1, right? We calculate the final value, 0.5, and this 0.5 into 1 is equal to 1. So h of p is equal to 1 for fair coin. Probability is half, and we calculated that 1 is the surprise, that is with negative log value. So we just sum that up, probability into log of probability of it, and probability into log of probability of it, negative log. So this is sums up to 1. So this is 1 bit, this is in bits. Okay, so this is your for fair coin. And then similarly h of p or entropy for biased coin, where p of h is equal to 0.9 and probability of tail is equal to 0.1 will be, let's do it again. So this will be h of p will be equal to summation. Similarly, so we've calculated all these values. So for heads it is 0.15 bits, so it will be 0.9 is the probability into 0.15 plus 0.1 into probability is 3.32. For tails the surprise is 3.32. So this is your heads, this is your tails, this is your heads, this is your tails. Entropy for each of the value. So if you calculate this, this will come approximately to 0.47 bits. So if you see here, the entropy for a fair coin was 1 bit, and this is 0.47 bit. This is low. Low entropy means low randomness, and that's obvious because here both the chances of getting a head and tail is equal, half half. That's why the net entropy or randomness is higher than a biased coin where getting probability of getting a head is very high, that's 0.9. So that's why the net entropy is lower than 1 bit, is 0.47 bit, that is less than half of it. Okay, I hope entropy or randomness is clear, because this is the base. So surprise, okay, you based on that surprise we calculated entropy. Entropy is average surprise. Okay, I hope entropy is clear.